All right, so let's go over section 3.0 today, rational functions. In this section, we're going to learn everything we can possibly algebra about rational functions. To do so, there's a handout in the note inside the notes. It says 3.6 handouts. It shows the steps that I'm going to go over each and every one of them. Okay, and I'm going to give you examples on each and every one of them. So on the test, you'll be asked to graph a rational function, and you're going to be listed. I'm going to say find vertical asymptotes. You're going to learn how to do all this. Okay, but it'll be listed for you, and you have open book. So let's go over this one step at a time. The first step is to find the domain. But before we do that, let me remind you what a rational function is. So a rational function, from the word ratio, which is a fraction, is of the form f of x equals p of x over q of x. So when you divide two polynomials, you get a rational function where p and q are polynomials. Q cannot equal 0 because that's in the denominator, are polynomials. So how do we graph rational functions? How do we graph rational functions? Of course, it's one thing to punch it in the calculator and see what the graph looks like, and it's another thing understanding every aspect of the graph. Okay, so our aim is not just to punch in the calculator. Punching in the calculator would be our last step to check our work against the graphing calculator, but we will go through every step. The first step is to find, if you look at the handout, you will find the domain, and to find the domain, the denominator cannot equal 0. So find its domain, and the domain of f of x equals p of x over q of x is all real numbers from negative infinity to infinity, except when q equals 0. Because if q equals 0, the fraction is undefined. Okay, all real numbers except when q equals 0. So for example, how do we find the domain of f of x equals x minus 2 over x squared minus 9. So we start out by setting the bottom equal 0. It's a quadratic equation. So x squared equals 9, x equals plus or minus 3. So the domain is not just 3 and negative 3. It's all real numbers except 3 and negative 3. So the domain of f, it's all real numbers except negative 3 and 3. So we go from negative infinity to negative 3. We skip over negative 3. Then negative 3 to 3, then 3 to infinity. That's what all real numbers except negative 3 means. All real numbers except plus or minus 3. Okay? And that's the interval notation. I strongly recommend you do it in interval notation. That's something we need to learn. So the first step in finding and graphing a rational function is to find its domain by setting the bottom equal 0 and throwing out all these values. Then we want to find what we call the vertical asymptotes. Vertical asymptotes. If you look at the handout, the line x equal a is a vertical asymptote if f of x goes to infinity as x goes to a. If f of x goes to infinity, basically a vertical asymptote, a dotted line, it would be like this. If as x goes to, so this is x equal a, as x goes to a, for instance, as x goes to a, this is a, as you're getting close to a, your y value is going to infinity. It could be negative infinity. It could be from this side, or both. Okay, that's what this means. Okay, so x equal a is a vertical asymptote if f of x goes to plus or minus infinity as x goes to a. That's the definition. Now, if this is the general definition. For rational functions, that's what we're dealing with. To find the practical way to find the vertical asymptotes for rational functions, only for those functions, is reduce, it's a fraction, reduce it first if possible, then set the denominator equal 0. And whatever values you get are going to be the vertical asymptotes, but you got to reduce first if it's possible. Okay, you got to reduce first if it's possible. For example, to find the vertical asymptotes of f of x equals x minus 4 over x squared minus 16. So first I would factor the bottom, difference of two squares, reduce it as long as I know x does not equal 4 because I can't divide by 0. Once I get that, then I would say x plus 4 equals 0. So x equal negative 4 is the only vertical asymptote of f. Okay, x equal 4. Negative 4 is the only vertical asymptote of the graph. Now you can check as an example. I want to actually punch that in your calculator on page 37 in the notes. Use a grapher and a t-table to show that f of x goes to infinity as x goes to 2. Again, with the shortcut that I showed you, reduce the fraction. It's reducible already. Set the bottom equal 0, x minus 2 equal 0 if x equal 2. So we know that x equal 2 is a vertical asymptote. But this shows you that the graph, punch in 1.9, these values. As x approaches 2 from the left, you get negative infinity. As x approaches 2 from the right, you get positive. This is more calculus stuff, okay? All right. So far, you look at the handout, we went over domain, vertical asymptote. To find the vertical asymptote, you reduce the fraction to lowest terms. You set the denominator equals 0, okay? Then horizontal asymptote. The line y equals b is a horizontal asymptote to the graph of f if f of x goes to b as x goes to infinity. Okay. So number 3, horizontal asymptotes. So the line y equals b is a horizontal asymptote to the graph of f if f of x goes to b, it equals b as x increases without large and absolute value. Now to find the horizontal asymptote, practically, this is theoretical, the practical way is let f of x, so we're dealing with f of x equals p of x over q of x, okay, where p is the numerator, q is the denominator. If the degree of the numerator, p of x, is less than the degree of the denominator, q of x, then the horizontal asymptote will always be the x-axis, y equals 0, is a horizontal asymptote. Like if this is, linear, this is quadratic. If this is quadratic, this is cubic. This is quadratic, this is fourth degree. As long as the degree of the top is less than the degree of the bottom, the x-axis will be a horizontal asymptote. So y equals x plus 1 over x squared minus 3. Horizontal asymptote is the x-axis. Why? Because the degree of the top is 1, the degree of the bottom is 2. Therefore, we have a x-axis as the horizontal asymptote. If the degree of the top equal the degree of the bottom, then the horizontal asymptote is obtained by dividing the leading coefficient of the top of p over the leading coefficient of the bottom, always, as long as they have the same degree. So you divide the leading coefficient of the top by the leading coefficient of the bottom, and that's going to give you your horizontal asymptote. So y equals 6x plus 3 over 3x minus 2. Same degree, top and bottom, so the horizontal asymptote y equals 6 over 3, which is 2. That's going to be your horizontal asymptote. And then the third case, if the degree of top, so we did top less than the bottom, top equal bottom, and top is greater than the bottom. If it's the case, then we have no horizontal asymptote. There's no line, horizontal line, where the graph goes along and never it goes along to infinity. Okay, there's no it. Instead, we have what we call slant or oblique asymptote. Slant or what we call oblique asymptote. And how do we find that? This will be discussed at the end of the class. Discussed at the end of the section later. Okay. So for example, y equals x squared plus x minus 1 over x minus 1. That's a 2. That's a 1. Degree of the top is greater than the degree of the bottom, so there's no horizontal asymptote. Instead, we have a slant asymptote, and later on I'm going to show you the slant asymptote is y equals x plus 2. I'm going to explain that later. Okay. All right, so let's assess where we're at right now. So we did domain, all real numbers except where denominator equals 0. To find the vertical asymptote, we reduce and then set the bottom equals 0. To find horizontal asymptote, we look at the degree of the top versus the degree of the bottom. If the degree of the top isn't the degree of the bottom, the x-axis is the horizontal asymptote. If they have the same degree, we divide their leading coefficients. If the top has a degree more than the bottom, no horizontal asymptote. We will have slant asymptote to be discussed at the end. Then we're going to do intercepts, x-intercept and y-intercept. So number 4, to find the x-intercepts, which we also call the zeros. Remember, and we've done a lot of zeros of f. You set y equals 0 and solve for x. So for example, y equals x minus 2 over x plus 4. To find the x-intercepts, we set y equals 0, x minus 2 over x squared plus 4 equals 0. To solve this, we times by the bottom to get rid of the bottom. X minus 2 equals 0. So the x-intercept, so the graph will hit the x-axis at the ordered pair 2, 0. Find the y-intercept. We set x equals 0 in the equation and solve for y. So if we do it over here, y would be 0 minus 2 over 0 squared plus 4, negative 1/2. So the graph will hit the y-axis at 0, negative 1/2. Okay. So we did that. Now, the graph will never ever cross a vertical asymptote, because remember, a vertical asymptote, remember, a vertical asymptote is, I don't know, because it froze a little bit. Okay, so I want to make sure I didn't miss anything. So I was reviewing, I don't know if we missed this, I can't rewind that. So I did the x-intercept and then the y-intercept. The x-intercept is obtained by setting y equals 0, and I did that. The y-intercept is obtained by putting in a 0 for x. I did it for this example. I got negative 2/4 or negative 1/2. Then I said a graph will never ever cross a vertical asymptote, because if it did, that means at x equal whatever, say negative 2 here or negative 1, there's a y value, but we know the function is undefined there. So a graph may never ever cross its vertical asymptote, but a graph may cross a horizontal asymptote, okay? Because that's a y value at x equals a, it could cross that. And how do we know? That's what we're going to discuss next. So a graph may never ever cross a vertical asymptote because it's undefined at those x values, but it may cross a horizontal asymptote. And if you look at the handout, the graph of f will cross its horizontal asymptote if the y value of the function equals the y value of the horizontal asymptote. If they intersect, their y values must equal. And then solve for x. If you can solve for x and get an answer, then they cross. If it doesn't make sense, then they don't cross. Okay? Okay. So for example, and then I'm going to show you one where it doesn't cross and one where it crosses. So look at this one. Y equals 4x minus 3 over x plus 1. So the horizontal asymptote, in case you forgot, they have the same degree. You divide their coefficients, leading coefficients. So the horizontal asymptote is y equal 2. So to see if the graph crosses its horizontal asymptote, that's a question mark, we set them equal each other. The y value of the graph equals the y value of the horizontal asymptote. So you times by 2x plus 1 to get rid of the fraction. 4x minus 3 equals 4x plus 2. It doesn't make sense because negative 3 does not equal 2. So the graph does it, or no, it does not. The graph does not cross its horizontal asymptote. And here's a snapshot of the graph. If you graph y equals, in parentheses, 4x minus 3 divided by, in parentheses, 2x plus 1, and then the horizontal asymptote is y equal 2, you can see that they're not going to cross. The graph goes along y equal 2, but it will not cross it. Okay? So, and we proved it algebraically. So now, let's look at example 2. Y equals 3x squared minus 5x minus 2 over x squared plus 4. Okay, if you find the horizontal asymptote, since they have the same degree, we divide 3 over 1. It's 3. Does the graph cross its horizontal asymptote? Set them equal each other. You can see I'll definitely have a question like this on the test. I mean, whether it crosses or doesn't cross. So times by x squared plus 4, just like we did in the previous one. So 3 times x squared plus 4. 3x squared minus 5x minus 2 equals, distribute the 3, that's 3x squared plus 12. That cancels out if you minus 3x squared, so you get negative 5x minus 2 equals 12. Negative 5x equals 24. Negative 14 over, negative 14 over 5. So the graph crosses its horizontal asymptote at negative 2.8, and the y value, of course, is the y value of the horizontal asymptote. Let's check that. So y equals, again in parentheses, 3x squared minus 5x minus 2 divided by x squared plus 4. And let's draw its horizontal asymptote, which is y equals 3. And bingo, graph. So this is the function. And this is the asymptote. And you can see it crosses right there, just about negative 2.8. So you can check your graph, okay? All right. The final thing that we need to discuss in... of course, and then you're going to do a t-table. So step number 7, you make a t-table if you have to. You have a grapher, you don't have to worry about that. And then you do the graph. And after I show you an example, then I want to show you the slant asymptote. So if I say graph g of x equals x minus 4. So on the test, I'm going to tell you to graph something, and then I'm going to write down what you need to put down. And each step is worth something, okay? So I would say domain, and you're going to write me the work for the domain. And in this case, x plus 2 equals 0. So x cannot be negative 2. So it's negative infinity to negative 2, which means the vertical asymptote is x equal negative 2. Why is that? Because remember, to find the vertical asymptote, you reduce. You can't reduce. X plus 2 equals 0. So that's going to give you the answer, okay? To find the horizontal asymptote, you look for the degrees, the degree of the top and the degree of the bottom. They have the same degree, so you divide their leading coefficient. So 1 over 1 is 1. And then the intercept, x-intercept, do y is 0. So x minus 4 over x plus 2 equals 0. You times by x plus 2 to get rid of the fraction. X minus 4 equals 0. So the graph will hit the x-axis at 4, 0. To find the y-intercept, you're going to put in 0 for x. So y equals 0 minus 4 or 0 plus 2. So the graph will hit the y-axis at negative 2. And then will the graph cross, and I will say that on the test, will the graph cross its horizontal asymptote? You're not going to say yes or no without explanation. Okay, so you're going to say the y value of the graph equals the y value of the asymptote. So let's see. Okay, the y value of the graph equals the y value of the asymptote. I'm sorry, the asymptote is 1, the horizontal asymptote. It's not negative 2. So x minus 4 equals x plus 2. Never. Okay, that doesn't make sense. So the answer is no, and there's a reason. You're going to state me the reason. And then you want a graph, number 7. So this is how I graph it. You're going to have graphing paper on the test. Just like usual. It's embedded in the test. So we have at x equal negative 2, we have a vertical asymptotes. The asymptotes should always be dotted lines. We have a horizontal asymptote at 1. We have an x-intercept at 4, 0. A y-intercept at 0, negative 2. And you can get a couple of values, t-table values. You're going to see the graph is going to look like this. It goes along the asymptotes, and there's another piece right here. How do I know? This is negative 2. Pick negative 3 for your x value and plug it in. You're going to see your y value is about there, and then you can do negative 4, so you can see it forming out. So make sure you do a perfect graph. Okay. Here's another one before we do the slant asymptote. So how do we graph? F of x equals x squared plus 3x over x squared minus x minus 6. Starting with the domain. Again, you set the bottom equals 0, x minus 3, x plus 2 equals 0, so x equals 3. So the domain is all real numbers except these values, so it's negative infinity to negative 2. So we're going to cover the whole number line, and we're skipping over negative 2 and 3. And now the vertical asymptotes. Remember how we do vertical asymptotes? We try to reduce it. This is x times x plus 3. And this is x minus 3, x plus 2. Nothing can be reduced. Okay? So if nothing can be reduced, then the vertical asymptotes are exactly what we got from the domain. If something is reduced, then whatever is cancelled out is not going to be a vertical asymptote. Okay? Because you're going to set the bottom equals 0 to give you these. So there's 2 vertical asymptotes. And then the horizontal asymptote. Remember what we do? We look for the degrees. They have the same degree. So we divide their coefficients. 1 over 1 is 1. And then the intercepts, the x-intercept, you put y equals 0. So you have x squared plus 3x over x squared minus x minus 6 equals 0. You're going to solve, so you're going to get rid of the fraction by timesing by this guy. That cancels out. X squared plus 3x equals 0. Factor out the x. So we have at 0, 0 and at negative 3, 0 are the x-intercepts. Then we're going to find the y-intercept by setting x equals 0. So y equals 0 plus 3 times 0 over 0 minus 0 minus 6, 0 over negative 6. So it's the origin, which we already got from the x-intercept. Now, will the graph cross its horizontal asymptote? Number 6. Will the graph cross its horizontal asymptote? Well, let's see. So the y value of the graph equals the y value of the asymptote. So we're going to times by x squared minus x minus 6 to get rid of the fraction. So x squared plus 3x equals x squared minus x minus 6. We're going to minus x squared. So we have 3x equals negative x minus 6. Add x. So that's 4x equals negative 6. Negative 6 over 4 or negative 3 over 2. So the graph will cross its horizontal asymptote at negative 3 over 2, and the y value of the asymptote is 1. That's where it's going to cross. And then if you graph it, putting all this stuff together, first the vertical asymptotes are at x equal 3, x equal negative 2. The horizontal asymptote y equals 1. The x-intercept 0, 0 and negative 3, 0. The y-intercept is 0, 0. And the graph will cross its horizontal asymptote at negative 3 over 2, 1. It will cross right here. So you can see, I mean, you can get couple more points between, you see a graph may never cross these two. Okay, so there's going to be a piece of the graph to the left of this horizontal asymptote between and after, because it has to cover the whole number line. That's the domain. That's what the domain is for. So the piece to the left has to go through this point. So obviously it's going to go along this line, along that line. If you're not sure, pick some t-table values from your calculator. Okay, now between these two, it has to go along this, through that, so it's going to go along that. It's not going to go back up because it will have to cross the x-axis, which it does not. So see how it's crossing its horizontal asymptote? We knew that. And now this piece here, we don't know if it's going to go here. We know it's not going to go here because it would have to cross the x-axis. So it has to go between these two asymptotes. Again, if you're not sure, 1, 2, 3, 4, find the y value. It's going to give you a value above 1, okay? And that's the graph. All right. Now, I want to talk about slant asymptote. On page 43 in your notes, slant asymptote. So remember, if the degree of the top, we're dealing with rational function. We said if the degree of P is less than the degree of Q, it's the x-axis that's a horizontal asymptote. If they have the same degree, you divide their leading coefficients. And if the degree of the top is greater than the degree of the bottom, then we have a slant or oblique asymptote. But how do we find that oblique asymptote? So to divide it, to find it, we divide using long division, P over Q, okay? And then y equals the quotient. Remember that when you divide, there's quotient and there's remainder. The quotient of the answer is the slant asymptote. So here's an example. 72, page 309. 72, page 309. So how do we graph f of x equals 3x minus x squared over 2x minus 2? We want to write it in order, so we're going to do negative x squared plus 3x, the highest degree first. Okay? We always do that so we find the asymptote, we don't get mixed up. So start with the domain. 2x minus 2 equals 0 if x equals 1. So it's all real numbers except 1, which means we're going to have a vertical asymptote at 1. Why is that? Because remember, you want to factor this first and then set it equal 0. Even if you factor it, nothing is going to be reduced. Okay, so you set it equal 0, it's going to give you the bottom equal 0, it's going to give you x equal 1. All right, and then horizontal asymptote. Since the degree of the top is more than the degree of the bottom, there is none. But there is what? There is a slant asymptote. How do we find it? Let's do it. We divide negative x squared 3x over 2x minus 2. We cannot do synthetic division here. That's why I said long division. So if you divide negative x squared over 2x. So you get negative 1/2 x. You put it up here. You times it by 2x, you get negative x squared. You times it by negative 2, you get plus x. You switch the signs in case you forgot. So that's 2x. And then you divide 2x by 2x, you get 1 plus 1. 1 times 2x is 2x. 1 times negative 2 is negative 2. You switch the signs. So y equals the quotient of the answer is a slant asymptote. So what is the slant asymptote? Y equals negative 1/2 x plus 1. You will see what that means when I graph it. Okay, so we did domain, vertical asymptote, no horizontal asymptote, there's a slant asymptote, and then the intercepts. So to find the y-intercept, x equals 0. So that means y equal negative 0 plus 0 over 0 minus 2, which is 0. To find the y-intercept, so the x-intercept, y equals 0. So 3x negative x squared plus 3x over 2x minus 2 equals 0. We times by 2x minus 2. We factor, so x equals 0, which is the origin, and x equals 3, which is 3, 0. So no horizontal asymptote, so we don't have to worry about the graph crossing the horizontal asymptote because there is none. So now if we want to graph it, we have a vertical asymptote at x equals 1. We have a slant asymptote at y equals negative 1/2 x plus 1. So when x is 0, y is 1. When x is 1, y is 1/2. When x is 2, y is 0. So I'm just plugging values in to get the slant asymptote. So the graph will fall between the slant asymptote and the vertical asymptote. It has to go 3, 0 is an intercept and 0, 0 is another intercept. And you can pick few values and you will see that the graph is going to go along the slant asymptote and the vertical, and the same thing here. And you can graph it and see that you have a grapher. You graph everything, it will show. Now make sure you practice finding the slant asymptote. I'm going to do one more example before I call it off for this section. So if I say find the slant asymptote, just that, no graphing, the slant asymptote of f of x equals 3x cubed minus x squared plus 2x plus 1 over x squared minus x plus 2. So we're going to do long division. Minus x squared plus 2x plus 1 over all that. So we're going to divide 3x cubed by x squared. We're going to get 3x, put it on top. times it. 3x squared, I mean 3x times x squared is 3x cubed. 3x times negative x is negative 3x squared. 3x times 2 is 6x. Switch the signs because we're subtracting. Negative x squared plus 3x squared is 2x squared. 2x plus negative 6x is negative 4x. And this guy is going down. 2x squared divided by x squared is 2 plus 2. Distribute. 2 times x squared. 2 times negative x, and 2 times 2, switch the signs, negative 4x plus 2x is negative 2x, that's negative 4, so y equals, you gotta write your answer like this, 3x plus 2 is the slant asymptote. What do we do with the remainder? Nothing, okay, it's just the quotient that's gonna give me the slant asymptote. And there's an example there that you need to do at the bottom of page 45, and that's it for graphing rational functions in 3.6 until 3.7. See you then.